Okay, I'm recording the lesson right now. So what is the deep geothermal energy? It's the, yeah, so we have to dig wells. We are talking about thousands of feet until we find a heat source within the earth. Okay, and then the temperature here is extremely high, so we can conduct water. The water boils and it generates steam, and that steam moves turbines and we generate electricity. Okay, uh, but this is the deep geothermal energy that happens when we have this kind of heat sources uh, available, and it doesn't happen in every single country. We have this in Iceland. Iceland is an interesting country. So they have this geyser. So they have these hot sources quite shallow. Okay, so they can afford to dig those holes, and they have plants, and they can produce this kind of energy. Okay, but that happens in Iceland and that happens in some parts of the United States, but it doesn't happen in everywhere. Okay, so we need to understand where we are. So that's why if we see the contribution of this deep geothermal energy, it's steady, so it's not growing, and it's very small. Okay, because we cannot use this everywhere. But wind and solar, they are growing. And what about the hydropower? Okay, hydropower, we have been using hydropower energy since the beginning of the 20th century. It's considered a renewable energy, but it doesn't mean that it doesn't have a huge impact, a huge environmental impact. I always show you this picture of okay, so there's a nice place between Spain and Portugal. So if we look at this, yeah, there you go. Okay, so this is the river Tagus in between Spain and Portugal. Um, and well, this picture is very interesting because this is a Roman bridge. So that bridge was built 2000 years ago. I think it was in the first century BC. Okay, so this bridge, it was built by Roman people, and it's been there for 20 centuries. Yeah, 2000 years. And just close to this bridge, you find this dam to generate hydropower energy. I mean, this is renewable. Once we have done this dam, we have renewable energy, and we can open these, we can move turbines, we can generate electricity, that's fine. But it has an impact. It has an environmental impact in the landscape and in the everything. Okay, so it doesn't mean that building dams, oh, it's renewable, oh, that's fine. Well, it's fine. I don't mean that it's wrong, but it has an impact. Okay, and here I think you can see the impact. You have this nice, if you look from this point to the bridge, you see it's like being in the, yeah, in the first century, you see. But if you look at the other part of this picture, you see, okay, what's that monster? But it's considered renewable energy, but it comes at a price. And then we have wind and we have solar. We all know what these wind generators are, and we know what PV panels are. Okay, they the impact of these two renewable energy sources is growing, but it's not even half. It's like 20, 25% of the renewable energy production. And the renewable energy production, it's about 10, 15% of the total energy production in the world. So this is where we are. Do we want this to grow? Yeah, I think it will be better if renewable energy grows, but so far we are here and we need energy. That's another option. We can live without energy. We can, yes, we can light our houses with candles. We can burn wood to heat up our houses, and we can walk. We don't need to use a car or planes. So we can move on that direction. I don't mean it's wrong. But if we want to continue to do what we are doing now, we need energy. And we have the Department of Energy in the United States. And everything that has to do with energy, this is the most reliable source. So if we click here, here we have science, innovation, energy. So that comes from the government of the United States. And here we have energy sources in clean energy. So let's find out what clean energy is. Clean energy. We have here a solar array, thousands of panels producing thousands of megawatts of electricity. So this is clean energy. Solar, it's clean. Wind generators are considered as renewable source, clean energy, whatever. Water, this is the hydro power. We can have these monsters, the picture I showed you before in Spain, or we can have these small waterfalls. We can generate some electricity with this, so it doesn't have to be something incredibly big. So we can have these hydropower plants with small buildings in these small waterfalls. Then we have the geothermal. So this is the geothermal. It's heat energy from Earth. This is what I told you. But we need to understand where this kind of geothermal energy is shallow enough to invest money on that, because it's too deep. It doesn't make any sense to do this. We have bioenergy. We have biofuel. Okay, so we can burn plants to generate well, to generate energy. It can be either electricity or whatever. So we have these biofuels. So this is clean. Okay. Nuclear. So nuclear is considered as clean energy, because all these, well, they have got they have cropped the picture here, but let's look at there you go. So here we have this. Okay, this is as I think I've told you before. This is not harmful. This is vapor. This is water vapor. Okay, so we don't have to be scared that oh, look at that smoke. So that this has to be. No, it's not dangerous. The dangerous things of nuclear plants, we don't see those kind of dangerous things. They are the waste, and waste is somewhere. Probably it's not even in this nuclear plant. It's somewhere else. Okay, but if we look at this, we say, wow, it has to be terrible. No, those are like clouds. This is vapor of water. Okay, so if we look at this from the Department of Energy of the United States, the nuclear power is a clean energy. Okay, so keep that in mind. And then we have hydrogen and fuel cells. I've been, I don't know, since well, since I've been interested in this kind of things, in energy, buildings, energy efficiency, I am, or they're telling me that hydrogen is the future. Well, we're in the future now, and hydrogen is not here yet. I don't know. I think it will be a clean source of energy and with zero emissions, and it will produce, if these hydrogen plants will produce a lot of energy. I don't know, maybe, but it's not here yet. Okay, so there are plans, and but the percentage of the energy that it's generated in these hydrogen plants, it's not relevant yet. Maybe it will be in the near future. But this is what clean energy is. Okay, so we have solar and wind. This is what we all think when we are thinking about renewable energy, clean energy, whatever. We have water, these hydropower plants, geothermal, biofuel, nuclear, and hydrogen. So what can we use in our buildings? Well, basically solar. Is it likely that we can integrate these wind generators in buildings? It's not. If we are living in the middle of nowhere and we have a small house and a large lot, maybe we can have these wind power generators, maybe. But in the middle of a city, we cannot have these kind of things. Again, with the current technology, can we have hydropower in our houses or in our buildings? Well, if you are living close to a river and you can build these small dams and you can, yeah, in theory we can, but it's not feasible. Can we use this in houses or in buildings? If we are close to a source like this, we can, but again, it's not. And can we use nuclear energy? Well, we use nuclear energy. We use the electricity that comes from nuclear plants, but we cannot create our own nuclear plant in our lot that I know of. So basically, we have to go solar. So this is the 90% of the renewable energy that we can integrate in buildings. It's about solar panels. So we need to be aware of that. And so if we want to integrate clean renewable energy in our buildings, if we study what the Department of Energy is saying about clean energy, and so the only thing we can do, or the only thing, the best thing we can do, probably is to install solar panels or to integrate solar panels in our buildings. What is this? Well, we are talking about these OECD countries. This OECD stands for the Organization for Economic Cooperation and Development. This it's a cool name. What does it mean? Well, it's an international organization of 34 countries that have a democratic system of government. Okay, so who's OECD countries? What countries are here? United States, Mexico, Japan, Germany, Turkey, France, United Kingdom, Italy, Korea, Spain, Poland, Austria, Chile, Netherlands, Belgium, Greece, Czech Republic. Okay, so here you have the list of countries. Is China here? No, it's not. Neither is India and other countries. Okay, so when we are studying these kind of things, well, because all these governments, in theory, they are on the same page when it comes to energy. So they are all moving towards the same direction. Some of countries are moving faster, other countries are moving more slowly, but they are all moving towards increasing the renewable energy in the energy mix of countries. Okay, but it depends. As you can see, the non-OECD countries, the part of renewable energy is not as much as in these countries. Okay. But we need to be aware of that. So this is a group of 32 countries, not that much, and they are all moving towards increasing their renewable production, their renewable energy production. That coal is still mainstream in most of countries. Coal is getting more and more important. Nuclear is important in OECD countries because it's a huge investment and some of the countries cannot afford to make those investments. Okay, but coal is still important even in this kind of countries. What is this? This is well, this is interesting. We have the top PV countries. in 2014, but this is the trend. So this is the countries that are producing more energy from PV panels, from solar panels. And China is the one who is producing the biggest amount of energy from PV panels. But we are comparing, or this is the total number. We are not comparing the total amount of energy that they are producing from renewable sources. Okay, but China, Japan, and the US, we have in these countries, we have the biggest amount of energy produced by PV panels. The other question is, what is the percentage of renewable energy in the USA? What is the percentage of renewable energy in China? That's a different question, okay? Well, this is interesting. That was happening in 2014. We need to update this information, but I don't think it has changed a lot. And that's interesting too. So this is how we produce solar energy. And as you can see, there are two different strategies. We have this is in the European Union. I haven't found information about China or the United States. I'll find out later. But I mean, it will be either to the left or to the right. But there are two strategies here. So we can either produce solar energy at large scale installations. What is this? It's the picture that we saw here. Okay, so this is a large scale. We are not talking about placing a couple of panels on the roof. So we have thousands of panels here in the middle of nowhere, and we are producing electricity here. So this is a strategy. And then another strategy is to produce electricity on your roof. Okay, so we have a lot of houses or buildings, so we can have the roof, we can place PV panels on that roof, and we can produce this kind of solar energy. So those are two strategies. Some countries like Romania and Spain, they have these large scale installations. Other countries like the Netherlands and Portugal, they have the residential or commercial roofs. Okay, so they are placing PV panels on roofs. They are not placing PV panels in the middle of. Why? Well, there are different. It has to do with the density of population in that country. So apparently there are a lot of empty space in Romania and Spain. So there are plenty of space for these huge installations. If you don't have, maybe it happens, as far as I know, in Portugal, in the Netherlands, they don't have large fields without any buildings, so they can't afford to do this. So they use the building roofs. In other countries, the UK or Germany, well, they have a balance between this and this. So there are objective reasons that explain those strategies, but there is also economic reasons and other interests in doing this. Okay, so we don't have to be naive. We don't have to say, okay, we will move to solar. We are all solar. We want to save the planet. Yeah, so this is what we need, but if it's not a good business, this doesn't work. Okay, so we will talk about this over this course, but we need to understand where we are. So if you are in Romania and you have an idea of placing PV panels on roofs, maybe it won't work, because in Romania, they have a different strategy. And if you want to install thousands of panels in the middle of nowhere in Portugal, it won't work. Why? Because country is not doing this. Okay, so we need to know where we are, and we need to know what, because it's not easy. It's not, there is not the right answer, and we don't have the same answer in different countries, or in different, or even within the same country. We can have different strategies in different states. So I need to find something like this in the United States, because in the United States, there are places in which we have a lot of people in a very small state, And in other states, there are huge areas without any people. So probably there would be strategies like this in different states in the US. So when it comes to solar panels, PV, photovoltaic panels, we have three technologies. We will speak about these three technologies: the crystalline, the thin film, and new technologies. Uh, we will speak about these later. But today, well, I want you to be aware of that. The world population is growing. The energy consumption and generation, it's growing much more than the world population. When it comes to energy sources, renewables, nowadays, it's around 10 to 15% of the total energy production in the world. And coal, which is the worst, the most contaminant, even the less efficient, but it's the biggest source of energy that we have nowadays. Then when it comes to renewables, we have hydropower, and wind and solar is growing. Wind and solar sources are growing. And well, all these countries, these 32 countries or OECD members, they are moving towards increasing the renewable production. And this is a trend, and it won't stop. Okay, I don't think, well, I don't think, but this is the trend, and we will increase the renewable production. And then there are different strategies. So if we are talking about renewable production, it depends on where we are. So there are different strategies to enhance the renewable energy production. It's not the same everywhere. And now we have to, when we are starting a project, imagine that you are architects and you have clients and you are committed to sustainability because you have been studying in King State College, and so you are committed to renewable energy, integrating renewable energy in buildings, improve the energy efficiency of buildings. Yeah, so those are goals that we have to achieve. But you have a client, and you have to talk to the client beforehand, before doing any single line with your pencil. You have to talk to the client about what the client wants. So is solar right for you? So that would be a good question. Okay, so yeah, so you want a house, or you want a building, or you want to develop a commercial building or a mall or a factory or whatever. Okay, so do you want solar energy in your building? And then we need to study all this. Before giving an answer, we have to study the site. Do you have a roof, a large area of a roof? If you want to integrate solar panels in your facade, or do you have a large lot so that you can have these large scale PV installations? Okay, so this is the first thing, the site. We need to know the site. What dominates the horizon? Are there mountains, towers? Yeah, because if we want to generate electricity out of the sun, we don't need any shade, so we don't need any obstructions. If we have trees, towers, mountains, if we don't have enough sun, maybe it's not a good decision. Then location. How much sunshine per year? We need to understand this. Okay, so we have to make the most of this. It's a huge investment. So will we make the most of that investment? So we need to know where we are. Then the jurisdiction. What is this? What incentives, tax credits, carbon reduction certificates, building regulations are in place in the country, state, or region? Okay, so we need to be aware of that. It's at a country level, state, or region level. We need to know regulations, because we can have deductions. We can have tax deductions. We can have, or maybe we have building regulations that force us to do this. So we need to know the law, because depending on the law, installing solar panels can be mandatory or not mandatory, or it can be a good business or a bad business. Again, we don't have to be naive. We need to know what is at stake here, especially for our client, because they are going to invest a lot of money. So we need to be aware of that, and probably they don't know anything about that. And then, well, this is the site, location, and the law. Can we control this? No, we can't. We can't control any of this, but at least we need to understand where we are in terms of site and in terms of laws. And then we have the motivation. So this is the conversation that we need to have with our clients. What is the primary motivation for going solar? Return of investment. What is this? Okay, so yeah, so I know that in this region or in this state, they have tax deductions, and if we invest in solar energy, we will return my investment in 3 years. Okay, is that the motivation? No, I'm not. I don't want to save the planet. I want to make money. Can you make money out of renewable energies? Maybe you can. Yes. Okay, so this is one motivation. Why not? Increase the renewable portfolio. Yes, some of the companies, they are moving towards renewable. Yeah, they want to be renewable, green. That's in fashion now, and they think that they can increase their business by having a renewable portfolio. Okay, so 80% of our plants are powered by solar energy, and we have an advertisement, and we say, okay, I will rely on this company instead of this company that is burning coal. Okay, so maybe there are clients that want to go or want to hire companies that are investing in renewable energies. Maybe that's a motivation as well. Hedge against fuel price risk. That's another motivation. Well, maybe you are young and you don't know that 15 years ago, the price of the oil barrel, it was above $100. It was close to $120, and that happened 15 years ago, or 10 to 15 years ago. Yep. Okay, so if the price of the traditional energy is extremely high, then you have to move to other sources of energy. Okay, and if you have a company or you have a factory and you depend on fuel, oil, gas, or whatever, what if the price of fuel increases a lot? Well, maybe your business is not feasible anymore. So what if you decide to, okay, in case if the fuel price goes up, I have my own solar array, and I can generate all the electric energy I need to run my company. Okay, that's another motivation. And another motivation: reduce carbon emissions. By reducing carbon emissions, yeah, we save the planet. So you might find clients. Okay, so we know that we are doing something wrong. We are harming the atmosphere, and we want to reduce carbon emissions. And if all of us contribute towards this goal, we will end up achieving that goal. If there are 5 billion people doing the same, reducing carbon emissions, the carbon emissions will be reduced. Okay, so maybe that can be a motivation. And then community feel good. Well, that's another motivation. I want to do something good for my community, and reducing emissions and stop burning fuel can contribute to have a better community. Okay, so all these are motivations. So what kind of client do you have? Do you have a client that wants to make the community a better place, or do you have a client who wants to return the investment as soon as possible? Well, we need to be aware of that. And then the application. What do we want to do with that energy generation? Electricity or heat? If we run our building with electricity, is it grid connected or is it off grid? Okay, so here we have to understand this. And do we have to combine this with other source? Because renewable energy, especially solar energy, it doesn't happen 24 hours a day. No, we can't generate solar energy during the night. So probably will need to combine this solar array with other energy sources. And finally, financing. How are we going to pay this? I'm going to pay, or your client is going to pay this with the savings, or we can have a bank loan, or we can have any kind of whatever. Okay, and that depends on the jurisdiction. Okay, so the financing and the jurisdiction, they are connected to each other. So before going solar, okay, so let's do this. No, you have to go through these questions, because if the site is not good enough, forget about everything else. So if you don't have enough sun in your site, there is no way that you can integrate solar panels in your buildings. Okay, so it's complicated. It's not a question of, I want to save the planet. Yes, I want to save the planet, but you have to build something in this site, and in this site you don't have any sun. So what's next? And why would anyone not buy solar? High financing cost. So the upfront cost, the money that you have to pay at the beginning of the project, if you install solar panels, it's much higher than if you had an oil boiler. It's perceived to be too intermittent. Yeah, it's true. Okay, so we don't have 24 hours of sun. So this is something that hinders the solar market penetration, because people think, well, yeah, but do I have to install batteries? It will be too complicated. No, it's better to have a boiler with an oil boiler or a gas boiler, and I'm sure that I won't have an interruption in our okay. And finally, no brand name. Well, now there's a brand name. We have Tesla, and they are solar, or they are not solar, they are electric. Before that, I don't think you have a brand name for PV panels. If I ask you, okay, give me a brand for PV panels, nobody knows anything. Okay, so PV panels are something that they don't have a brand, and that if you want to create a product, that's something that you think about. There's an opportunity here, by the way. So if you don't know any brand name for building solar integration or renewable energy integration in buildings, there are two reasons. The first reason is that nobody has done it yet, because nobody has thought about it, and maybe you are the first. And if you create a good brand, think about computers 30 years ago. Now we have different brands, and we want this because there's a market campaign, and we have a logo, a nice logo, and we want that in our computer. Okay, that's perfect. Do we have this in residential buildings with solar energy? I don't think so. So if you are the first in creating a brand with a good product, maybe you can. So that's the first option. Nobody has done it yet. And the other option is nobody has done it because it's impossible and it's not worth it. I don't know. And we will study something about this. So this is the payback period. As you see, if we are in the right side with the right geographic location, with law that encourage people to do this, we need to talk about finance. And this is a formula that we need to understand. This is the internal rate of return. and it has to do with the net present value. If we make an investment right now, today, what will be the value of that investment in 10 years, 20 years, 50 years? Well, we need to know about this. Okay, so I told you that we don't have to be naive. Of course, I'll show you that we can save energy. Saving energy, it's good for the planet and for the community, but you have to show your client that they will be able to save money in a time period. How much time? I don't know, if I'm 40 and I want to invest in solar energy, you say, no, in 50 years, you will recover your money. You say, what, 50 years? Most likely I won't be here in this world. Okay, what about 40 years? 40 years, yeah, maybe I'm there, but I will be 85. And yes, I will recover my investment, but what can I do? No, 10 years, 10 years, perfect. Okay, so everything that it's below 10 years for this return of investment works well. If it's more than 10 years, it's like 10 years. I don't know, 10 years is too much. So we need to be aware of that as well, because it's important. Okay, so this is an introduction. So today we are going to talk about this, and this is what we will be learning today. And by the end of today, you should be able to analyze detail in terms of this, the thermal breach and the moisture. Okay, what is a thermal breach? This is a thermal breach. A thermal breach is a place in our building or area in our building envelope in which we don't have thermal insulation. Okay, so here you have the wall. This yellow stuff is thermal insulation. There you go. And here we interrupt the thermal insulation. So this is a thermal breach. We can use thermal cameras to find out if we have thermal breaches in our wall. If we take this picture, we see that the studs and the horizontal structural elements, they are thermal breaches. So we have this orange area in which most likely we will have thermal insulation, but in these studs, we don't have any thermal insulation, and the temperature here is lower than the temperature in this orange area. Okay, so the temperature here is 16. The temperature here is 13. We are talking about Celsius. Anyway, but this is colder than this. So we have a building and we don't know because we don't see the thermal breach. We need the thermal camera to find out whether we have thermal breaches or not. We can predict this, so that's why we need to use Therm. Okay, so this Therm, this is the software. And here we can see where the problem is. So if we have this corner, we can understand that there's a thermal breach here because of the colors. Okay, so this is what Therm can do. And that's why it's interesting, because we can predict what's going to happen in terms of thermal breaches without doing this. Now we have the building there, and now we have to spend a lot of money in solving this thermal breach. By doing this with Therm, we can understand if we do have thermal breaches or not. And not only if we have thermal breaches or not, if they are relevant in terms of energy efficiency or not. Okay, but usually we have thermal breaches when we connect a vertical surface and a horizontal surface, or when we have a corner. So those are elements that are likely to have thermal breaches if we don't know how to solve them. And this is design. Okay, at the design stage, we have to solve this, and then we have to simulate it with Therm. And if we do this, at the end, we won't have these kind of pictures with our thermal camera. So why are thermal breaches a problem? Well, first, we lose heat. If we are talking about heating season in winter, we have thermal breaches. We lose a lot of heat through this area of the building. Then we can have unwanted heat. That happens in summer. In summer, it's the other way around. We have hot weather outside, and part of that heat is entering the building. We don't want that in summer. We can have cold internal surfaces. And this is wrong because when we have cold internal surfaces, condensation can happen, and then it may lead to mold, or I think it's mold or mold. Okay, it's a mold. This is mold. These are living beings, living creatures that appear in our walls. Okay, so that can happen because we have cold surfaces inside. We have thermal breaches. Well, here it's not a thermal breach; it's the whole world. But usually we have this when we have thermal breaches in our building. Okay, it's scary. But well, mold. It's we have mold. Yeah, this is mold as well. Okay, so French people, they are manufacturing cheeses, and they are proud of this. Okay, so this is mold as well, and some kind of mold, we can eat them, and that's fine. But usually, this is we don't eat these kind of things that appear in, and it tends to appear always in connections between walls and slabs, corners. Okay, so we have these kind of things. We don't need a thermal camera to understand that there's an issue here. So most likely there will be a thermal breach here because we have mold. Okay, so that's one of the risks of these cold internal surfaces. And then we have risks to comfort and health. Yeah, these kind of living creatures, they can cause health issues. Okay, so we have to prevent this from happening. So that's why thermal breaches are a problem. And this is what happens. Okay, so this is the famous mold. Always here, this is a connection between a wall and a window. So we have an area here. Probably the thermal insulation is not good enough. And we have these kind of problems. Why does it happen? Because we have indoors and outdoors. Indoors, we have a comfort temperature, and we have water vapor. So there, just by breathing, we are expelling water vapor. If the concentration of water vapor is too high inside, it tends to go out. And it tends to go out, and it goes through the envelope of the building. And the temperature is going down until the outdoor temperatures. If by any chance we get to the dew point within this wall, this we have the interstitial condensation, and well, this is what causes, eventually it causes this mold, this stain. Or so this is it. First, we need to prevent this from happening, an excess of water vapor. We can do this with ventilation. That's why the ventilation system, it's very important in buildings. If we have a good ventilation system, we won't have an excess of water vapor inside, and we won't have these kind of condensations. What if we don't, what if even if we have a good ventilation system, we have a great source of water vapor inside, we can have a bathroom, for example. Imagine a bathroom. In a bathroom, if we have a shower with hot water, we will produce a lot of vapor here. So it tends to escape. So what happens? Okay, so we need to provide this envelope with different layers to avoid this. And this is what we're going to start studying today. Okay, but this is not about the thermal transmittance. if you remember something about building science 1, um, I think I taught you how to calculate the thermal resistance and the thermal transmittance of, the thermal transmittance, this U value, it's 1 divided by the total thermal resistance. Okay, so first we have to calculate thermal resistance of this wall with different layers, and then we have to calculate the thermal transmittance. And you remember that we had a limit for the thermal transmittance because we had to meet the passive house requirements and all that stuff. Okay, so today I have to remind you of this because we have to calculate this again. But we will go further. It's not just calculating thermal resistance and the thermal transmittance of this wall. We have to calculate the temperatures within the wall. We have different layers, material 1, material 2, material 3. We have indoor temperature, outdoor temperature. So we have to calculate these temperatures within or at different interfaces of this envelope. And this is what we are going to do today. How can we calculate this? Well, there's a formula. And this is the formula. We have that the difference of temperature between two interfaces. Okay, so this is TS1 and TS2. So this can be TS1 and TS2. So this difference of temperature equals the thermal resistance of that layer, the thermal resistance of this material, divided by the total thermal resistance of the wall. So we have to add up the thermal resistances of all these layers, and this is the total. And we have to multiply this times indoor minus outdoor temperature. Okay, so quite easy. This is the formula, and this is what we are going to apply today. We have to calculate the thermal resistance of the wall, and then once we know the total thermal resistance, we know the thermal resistance of each layer of the wall, and then it's the thermal resistance of each layer divided by the total, multiplied by indoor minus outdoor temperature. So indoor minus outdoor temperature. Okay, so the formula is not complicated, but we need to remember what we were doing. I don't know if you created your own Excel file to analyze the thermal resistance of this envelope. Okay, so I have been developing this tool, and well, here we have in this column we have the materials. In this column we have the thermal conductivity. In this column we have the width, and here we have the thermal resistance as a result. The total thermal resistance is, we have to add all these up, all these values, and this is the total thermal resistance. And finally, the thermal transmittance is 1 divided by the total thermal resistance. Okay, so I want you to use this Excel tool. So far today, we will calculate only this, the total thermal resistance, but I will explain you how to calculate this graphic. Okay, so in this graphic, we have to compare two different things. We have to compare the temperature within that wall in different layers of that wall. This is the column. We have to compare it with the dew temperature, the dew point. Do you remember this? I mean, yeah, you should be remembering this because most of you have taken 370 systems last fall, and we use this tool to calculate the dew point. So you remember that we have to go to settings we can use English. Okay, so here, just by calculating the indoor temperature, let's say 70, and the relative humidity, let's say 50%, we submit this, and this is the point in which we are 70 Fahrenheit, 50% of relative humidity, and here we have the dew point. Okay, so what is the dew point? Let's refresh. The dew point is the temperature to which air must be cooled to become saturated with water vapor. When cooler, the air will condense to form liquid water. Okay, so this dew point or dew temperature is the temperature at which the water vapor condenses and turns or forms liquid water. Okay, so this is what this is our goal. We don't have to produce liquid water within our wall. Okay, so we need to know where the dew temperature is, and if we have this, look at this graphic. In this case, the orange line is the dew point or the dew temperature, and the blue line is the temperature of the wall in different layers. So if at one of the layers the dew point is higher than the temperature, then condensation happens. Okay, so this is a very useful tool because we can type here the name of the material, the properties of the material, and immediately we understand if we have risk of this condensation. Okay. I will explain this later next week, not today, because today we are going to focus on this column. We are going to calculate the temperature within this wall. We are not calculating the dew point or the dew temperature yet. So what do we have to do? Well, first we need to state here the indoor and outdoor conditions. Okay, indoor temperature, it's always around 70 Fahrenheit. It can be 70, it can be 72 or 69. It depends, but it's always around 70 Fahrenheit. This is always a good indoor temperature. What about the indoor relative humidity? Well, it's between 40 and 50. The relative humidity, 70 Fahrenheit and 40 to 50% of relative humidity, it's fine. It's a good condition. It's comfort condition. Okay. So here we can control this. Then we have the outdoor temperature, and the outdoor relative humidity. Where can we find this? Well, I showed you a lot of websites to calculate this. So let's say Keene dry bulb temperature. No, it is not. Keene. Okay, so we have access to this in AccuWeather. We have the humidity. This is the relative humidity, 47. The outdoor temperature is -7 Fahrenheit. I know this is Celsius. Yeah, so be careful with this. This is Celsius. Anyway, it's cold. This is the outdoor dry bulb temperature. This is the outdoor relative humidity. So we can find this in different sources. Okay. So we need to know where we are what is the minimum outdoor temperature we can have, and what is the average relative humidity that we can have there. So this is the first thing that we have to find out. Indoor conditions. Indoor conditions are always the same, are from 69 to 74. Relative humidity, it's from 40 to 50. And outdoor relative humidity, it changes. If we are in Miami, this is not, it will be warmer, and probably the relative humidity will be higher. Okay, so we need to know where we are. Anyway, so far we are going to use only the indoor and the outdoor temperature. So let's say that indoor is 70 and outdoor is 20. Okay. And here we have the list of materials. Do you have any questions, by the way? No, not yet. If you have any questions, you can interrupt me, or you can use the chat or whatever. So what do we have to do here? We have to type the materials that we have. You remember that we always had an interior air layer. So this is air interior and air exterior. If we have only 3 materials, 1, 2, and 3, in the rest of materials, you can leave it blank. And this is the thickness of the material. You type 0, and that's it. Okay, so it's, but the problem is that if you type 0 here, well, everything goes wrong, because eventually we have to divide the thickness or the width divided by the thermal conductivity. So if we divide 0 by 0, well, the software, the Excel file goes crazy. So that's why here we need yeah, you can type 1 if you have an empty layer. If you don't have any material here, you only you can type 1, but the width has to be 0 here. And then here we have the plywood, thermal insulation, and brick. Those are 3 different layers, and we need to find the thermal conductivities and the width. The width, it's something that we decide. Okay, so we are going to study this detail. So we have the indoor temperature is 70 Fahrenheit. And then we have plywood, 1 inch, fiberboard, that's a thermal insulation with 5 inches, and brick, 4 inches. Okay, so we are analyzing this wall. Okay, so how can we use this Excel file? This is inside and this is outside. So the first layer is plywood, 1 inch. Okay, so I type here plywood. The width is 1 inch. And what about the thermal conductivity? Okay, so you have another tab here. If you click here on thermal conductivity, here you have the thermal conductivity of different materials. So there is a long list of materials, and we have to find, let's say, plywood. Okay, so plywood, it's 0.8. This is the thermal conductivity of plywood. So you go back to this temperature distribution, and this is 0.8. Okay, so we have 1 inch, 0.8. Next, thermal insulation. So you have 5 centimeters, 5 inches of thermal insulation, and the thermal insulation is fiberboard. Okay, so here we have to type 5 inches. And what about the thermal conductivity of the fiberboard? So we have to find here fiber insulating board. It's 0.27 or 0.277. So here we type 0.277. It rounds up, it's 2.8. Okay, doesn't matter. And finally, we have brick. We have 4 inches of brick. So we have to find brick, common building brick. The thermal conductivity is 5. So here we have to type brick 5. And what about the width? Okay, so there is something wrong because the width, according to this, is 4 inches. So we have to type here 4 inches. and we only have 3 layers. Oh, by the way, this air int and this air ext, if you remember, we had this coefficient for walls, roofs, and floors. So this H coefficient is the heat radiation convection coefficient, H. And this is inside is 1.6, outside is 2.93. And well, the thermal resistance of this layer okay, so this first thermal resistance will be 1 divided by, and this is the interior air layer, so it's 1 divided by 1.6. How much is this? 1 over 1.6. It's 0.625. Okay, this value we have here. And then for the external layer, that will be 1 divided by 2.93. .93. So 1 over 2.93 is 0.34. Okay, so that's why here, if you're working with walls, you don't have to change this. It's the air int layer, the thermal resistance is going to be 0.625, and this is going to be 0.34 always. You don't have to change it. Okay. So now the thermal resistance of each layer is just the width divided by the thermal conductivity. So is this cell divided by the thermal conductivity, and that's it. You can calculate all these, and this is the total thermal resistance. If you click here, this is the formula. You are adding up all these columns. If it's 0, it's 0, doesn't matter. Okay, so let's work with this file and this one. Well, I did something wrong because this brick is 4. Okay, so that's why this is 0.8. Okay, I'll copy this again. So what do you have to do now? You have to, as always, we have to prepare reports. Okay, so this is the detail that you have to analyze, and this is the Excel file that we are using. So you can always copy this. Here we have the list of materials and the total R value. So you can just copy, Control C, and then on the PowerPoint, you can paste it. And if you select this, we have a nice format. Okay. And now to change this, because this is not 1, this is 0.8. And this is 21.07. Okay, so the total thermal resistance, it's 0.625 plus 1.25 plus 18.05 plus 0.8 plus 0.34, total 21.07. Okay, so I'm not asking you to calculate this by hand. We did this in Building Science 1, but I assume that you know how to do it. because you passed the course. So even if you don't remember, now you can use directly the Excel file. Okay, so you only have to type here the material, you have to type the width, and you have to type the thermal conductivity that you find in this list here. And then you have to copy this table on this PowerPoint. Okay, so this is what we, this is the first thing. You should remember how to do this. Anyway, if you don't remember, you can get back to me. I will explain it to you again, but individually, because I don't want to explain this because you are supposed to know how to do this. This is new. Okay, so this is what we are going, what we are doing now. So I'm going to delete this. So this is the total thermal resistance with different layers. And now we need to apply this formula here. You remember that, where was the formula? Yeah, this one. Okay, so we have the thermal resistance of a layer, the total thermal resistance, indoor minus outdoor temperature. And this is it. So now we have to calculate T1, T2, 3, and 4. Okay. So let's do it. T1 is the indoor temperature. So it's always the temperature that we want to calculate is the previous temperature minus all these, the thermal resistance of this layer divided by the total thermal resistance, and indoor minus outdoor temperature. Okay, so let's do it. What is the indoor temperature here for T1? Indoor temperature is 70. What is the first thermal resistance? It's 0.625. What is the total thermal resistance? 21.07. And then this is indoor minus outdoor is always 70 minus 20. So what is the temperature there? So I'm going to use the calculator. So it's 0.625 divided by 21.07 times 70 minus 20. Okay, so the temperature here would be 68.51 Fahrenheit. Okay, so T1, the temperature here is slightly below the indoor temperature. Okay, so the indoor temperature is 70. This is 68. The temperature of the wall surface is not the same as the air temperature. It's slightly below inside, and it's slightly above this temperature outside. Okay, what is the second one? What is the temperature after this plywood layer? So it's T1. So T1 it's 68.51 minus the second thermal resistance. The second thermal resistance is 1.25. The total is 21.07 times 70 minus 20. And how much is this? Let's find out. 1.25 divided by 21.07 times 50 minus 68.51. Okay, so this should be 65.54 Fahrenheit. Okay. What is the temperature 3? So it's the temperature 2, 65.54. The third thermal resistance, 18.05, divided by the total, bracket. And what is this? 18.05 divided by 21.07 times 50 minus 65.54. So this is 22.70. Number 4, the previous temperature. The fourth thermal resistance is 0.8 divided by the total. So this is 0.8 divided by 21.07 times 50 minus 22.07. Okay, this is 20.17. And finally, if everything goes well, if I do this, this number has to be 20. So let's find out. This is the previous temperature, T4, the last thermal resistance, 0.34, the total thermal resistance, 21.07, this. So this is 0.34 divided by 21.07 times 50 minus 20.17. Well, it's 19 point something, but it's very close to 20. So if we look at this, okay, if you look at this temperature, this column, the results should be the same. So this is, the first one is 68.51, here 68.52, okay. The second one is 65.54, this is 65.55, okay, that's fine. So this is 22.7, this is 22.71, that's fine. And there might be something wrong here because this is 20.81 and this is 20.17. Let's do it again. 8 divided by 21.07 times 50 minus. Okay, that's better. Yeah, so there's a mistake here. This is 20.81 and this is 20.81. I made a mistake here. This is 20.81 and now this is 20. Okay, so basically, if you want to do it by hand, you have to do this. You have to do this 1, 2, 3, 4, 5 times. You can check if it's right or wrong, because if the last temperature is 20, that means that it's correct. If this is not 20, that means that you have made a mistake somewhere. But if you use the Excel file, you can make sure that you haven't made a mistake because it's the Excel file. Okay, and this is the blue line is the temperature here. So if you place your mouse here, so you see that this temperature is 62.52, is 68.52, sorry. This temperature is 65.55. This temperature is 22.71, and this temperature is 20.81, and this is 20. Yeah, this is 20. Okay. So let's do it again. So this is the first exercise. What would you have to do now? You have to do something like that. You have to draw a line, and then you have to place T1, T2, T3, 4. And here I have the temperatures. So let's do it again. Let's use this wall. Now we have 1, 2, 3, 4, 5, 5 layers. We have 1 inch of plywood, 2 inches of glass wool. This is inside and this is outside, by the way. So plywood, glass wool, then we have plywood again, 1 inch. Then we have glass wool, 6 inches. And then we have plywood, 1 inch again. Okay, so let's do it. We have inside, and the temperature, it's 70, and the outdoor temperature is 0. So first thing, we have to type 0 in the outdoor temperature. Okay. Then we have to change the materials. Now we have plywood, then we have glass wool, then we have plywood again, then we have glass wool again, and finally we have plywood. Okay, so this is the list of materials: plywood, glass wool, plywood, glass wool, and plywood. Then the widths. The width of the plywood is 1 inch. Okay. The width of this first layer of glass wool is 2 inches. I type 2 here. Plywood, 1 inch. Glass wool, now it's 6 inches. And plywood, 1 inch. Do you have to do anything else? No, you don't, because here we have the total thermal resistance. It's 16.64. So here we should copy all these. We can paste it. Yep. Okay, so here you have the thermal resistance of all these layers. And now we should work with these lines. Yeah, maybe there's a better way to do this. But this is T2, T3, T4, and finally this has to be 0 because it's not 20, it's 0. Okay, so this is well, this is too small. That's 1, 2, 3, 4, 5, and 6. And we can move this here. And there you go. Okay, so we have all these temperatures. You can either calculate this by hand with this formula, or you can copy this column. Oh, sorry, because I haven't, we changed the width, but we didn't change the thermal conductivity. Okay, so we have plywood. Let's check that plywood is 0.8. Plywood, okay, it's 0.8. Then we have the glass wool. What is the thermal conductivity of glass wool? glass wool insulation is 0.23. So this is 0.23. Plywood is again 0.8. Glass wool is again 0.23. And plywood is 0.8. Okay, so let's check. This, we have 1 inch of plywood, 1 inch, thermal conductivity 0.8, glass wool 2 inches, glass wool 2 inches, thermal conductivity 0.23, then plywood 1 inch, plywood 1 inch, thermal conductivity 0.8, plywood, the glass wool 6 inches, 6 inches, the thermal conductivity 0.23, plywood, finally 1 inch, thermal conductivity 0.8. Okay, so everything is correct. And now we can type these temperatures. We can say that this is indoor temperature. This is T1. This is T2. T3. T4. T5. This is T6. And outdoor temperature is 0. There you go. Okay, so first, we have to analyze the wall. We have different layers here. Second, you have to use this Excel file, and then you have to type layers. You have to type the width, and then you have to find the thermal conductivity. So the thermal conductivity is on that list. Okay, so you have to go to this blue column, and you have to type whatever value we have for thermal conductivity here. We will end up calculating the thermal resistance. Then you have to copy all this table here so that I can check that you have typed the right materials, thermal conductivity, and widths, and this total thermal resistance. And finally, if you copy this column, from indoor temperature, that should be 70. The outdoor temperature, the last one, should be the one that you have typed here. And this is the temperature distribution within the, so we have in this case, 1, 2, 3, we have 6 different temperatures because we have 5 layers. And here you have the 6 different temperatures that we have in this wall. Okay, so now you have to work with this classwork. Nope, not this one. There you go. Okay, so I'm going to give you three different walls. This is outside, this is inside, plywood, glass wool, brick. If you have an air layer, you can see that in this thermal conductivity, at the beginning we have air. Okay, so we do have a thermal conductivity for air. So when you see air here, we have 2 inches, and we have that thermal conductivity. Here we have aluminum, air, brick, cellulose. Do we have cellulose here? Yep, we have cellulose. Gypsum board. Do we have gypsum board here? Yep, gypsum board. And here we have plywood, cellulose, and gypsum board. Okay, so there are 3 walls. So I want you to give me like 3. That would be wall 1, and I want the detail, the different layers of the wall with the names and the widths, indoor and outdoor temperature. This table that you can copy from the Excel file, and then this list of temperatures that is taken from this column here.